All right, you're
Yeah.
ready to go.
All right. So hi everyone, thanks for having me. I'm Juan and I'm a PhD student at Columbia, advised by Professor Pierre Jutin. I'm kind of going to share a little bit about like some of the recent works on deep operator learning for emulation. I'll also give a kind of like work in progress example for aerosols, uh, and as well for causal inference. So if you have any questions, feel free to raise your hands or maybe towards the end of the presentation. So the idea kind of like for operator learning, this is just a broad overview, is you want to be able to learn this operator H. We kind of like set this up in a differential equations, which is very common for a lot of climate and weather applications. And with some epsilon, which is just noise term here. There are quite a few recent advances for kind of like neural operators, like probably you've heard of this Fourier neural operator and this kind of thing that powers a lot of these weather emulators. And there are also quite a bit of resurgence for projection-based kind of like neural operators. And I'm going to discuss mostly on Koopman, but there are other emerging frameworks like the Morris-Swansig kind of like projection operators, which just have a lot more like bells and whistles to it. But we'll start with Koopman first and many others. So just a little bit of primer for Kuman theory. It's pretty beautiful, I think, in my own personal point of view, where on the left-hand side here, you have like some non-linear kind of like manifold. And then on the idea is you are projecting it to a linear manifold where your states now from X to Y is approximately linear. So this is nonlinear dynamics F, finite dimensional state, and linear like dynamics that are governed by this operator K. But of course, it's not. There's no free lunch here. The trade-off is that normally it has to be infinite dimensional transformation of X, which we call observable Y. So there are a lot of like different ways to go from the left-hand side to the right-hand side here. A lot of the common techniques like dynamic mode decomposition or extended DMD, where you have some kind of like nonlinear transformation of your feature X. It can be your autoencoder, let's say latent vector from some neural network outputs, and many others. So why we kind of like go forward with this, but we are gonna mention some caveats here. So the one of the advantages that is linearized approximately. So we are able to perform many textbook methods like linear stability analysis. So things like tipping point detection is pretty commonly used and applied here. And things like Granger causality, which we are going to formalize this a little bit more, which we term as Koopman causality. But as I mentioned, kind of like earlier, there's no free lunch. The heavy lifting is shifted from, classical problems of nonlinear dynamics, like there's a lot of time scale mixing, etc., to learning the appropriate transformation of X to Y, where their dynamics are approximately linear. But of course, with deep learning, the challenges can be easily reached nowadays because transformation, there's a lot of like, tools nowadays like autoencoder where you have some latent representation and so on and so forth. So I'm gonna discuss a little bit about like two use cases of like this operator learning. First is Koopman plus generative AI. I'm gonna set it up in the context of forecasting problems. I'll also set it up for emulation problem for aerosols. And two is, if you have time, I'm probably also try to link it to one of the recent work that we are doing is to bridge this gap of Koopman plus Granger causality. So we define a new class of causal inference for called Koopman causality. So this is the first case, subseasonal to seasonal climate forecast, and gonna give us brief aside on aerosol emulation. So this is just a brief overview of like some of the problems here. This is a nice diagram from one of the center here at Columbia, where there's an extreme gap between the weather and climate timescales. And this particular timescale has a lot of like problems related to like cyclones activity, wildfire, and so on and so forth. And if we kind of like, I just did a quick search on Google Trend, the trend of like weather AI and climate AIs are emerging. So naturally, can we use kind of like ML to be able to fill in this gap of S2S time scale. So this is from our work last year, trying to benchmark all of this weather emulators and try to find pitfalls and how we can kind of extend the predictability range from weather to subseasonal scale. One of the challenges that we found is that, and probably it's also common for everyone, familiar to everyone, is that it gets blurrier as the forecast time increases. And if you decompose this into their spectral kind of profile, you can see that like the blue spectra here and the orange spectra 6 weeks ahead, it kind of loses energy. And this kind of captures some of the blurriness that comes from this. So we kind of come up with this benchmark where instead of just having surface atmosphere, ERA 5, we collect a bunch of other analysis products that makes it a more, so people can just emulate the whole Earth systems. So that's kind of the idea here. So we are trying to bridge this gap. We have some ideas how we can bridge and improve the blurriness of the forecast. So this is just inspiration from turbulence decomposition, where most of the dynamics can be, for instance, represented by the mean component and some fluctuating flow. In a lot of the literature, this is called the closure term. And what we do is essentially we model the mean component with something like a reduced order model, like the deep Koopman operators, and the fluctuating flow, we can kind of model it with some diffusion-based modeling. So that's kind of just the general idea. So the general idea is with this reduced order model, we can generate a bunch of coherent flow, just reduced order kind of flow. And then using diffusion, we can do the correction to give us the final product. So this is kind of the general idea. So we are kind of showing in our work that, so these are two use cases for cosmograph flow and shallow water equations. What we found is that the diffusion kind of process is fixing this one is the large scale pattern, so low wave number, and then at the correction step, which they call it the diffusion step, it kind of also corrects some of the blue high frequency signal that gives you high fidelity kind of outputs. And this is conditioned based on the mean state flow that is estimated from the Koopman operators. So we are able to kind of have this high fidelity forecast. And also this is just a visualization over time where the top row is the truth. And then this is the reduced order model outputs. It doesn't have to be perfect as long as it gives good patterns, large scale patterns. And then with the diffusion, this is intermediate diffusion step, and this is the final posterior estimates. We are able to get high fidelity kind of outputs. So this is just the same thing, but we are plotting the spectra of the output. So this green as well as red lines are state-of-the-art kind of emulators, neural ODE or the Fourier neural operators. And what we found is that it currently captures some of the high frequency signals. So that's good. And this is just a visualization of the state-of-the-art Fourier neural operator. It seems to be losing energy. So that is a good sanity check. And we are also sanity checking against how stable in terms of the accuracy of the ensemble forecast. So this blue and orange are just two instantiations of our framework, and it's stable over long rollouts. So that's promising. And this is just similar analysis for shallow water equations, where this is just the reduced order model outputs, and this is the final forecast or posterior. Similarly, this is for some state-of-the-art FNO model emulators, and we are also seeing similar performance improvement. So this one is just probably not as important for the talk, but wanted to show how this framework is also robust if you have your prior to be kind of partially observed. Probably this is more relevant, let's say for data assimilation, where you have radar stations which are scattered all around the world, and you only have those kind of priors, and you want to reconstruct like the full state, and we are able to like do that with diffusion. I think this has been like used a lot in like data simulation. So, but we are just showing that this is also practically applicable for our use case. So moving back to our subseasonal, so the previous one was just trying to like make sure that everything works, and then our kind of like intuition is okay. So what we have now is being able to forecast over long lead times. So the middle second row here is kind of like the control run produced by this is ClimaX, one of the state-of-the-art model. And we are able to use this as our conditioning prior to be able to generate kind of like different ensemble realizations of the field. And so because this diffusion-based modeling, so it's a little bit cheap to be able to produce this. But of course, I think one of the key challenges of S2S is going beyond like statistics, because a lot of the applications are for regional forecasting. So if we just have this kind of like blurry outputs, if you want to zoom in into a specific region, it's not going to be helpful. So we have to be able to produce this kind of physically realistic outputs as well beyond the statistics. So that's one of the key idea here. And we are just like benchmarking against competitive with a few weather prediction centers like NCEP from the US or ECMWF, or yeah, we're just showing for two, but we're also benchmarking against like the China Meteorological Agency and the UK Met's office. The goal here is not to kind of like outcompete every single one of this, but we are showing the plug and play nature of it, because in this setup, we are just training one diffusion model, and then we can plug in any prior estimator. So any AI NWP that you want gives you a good prior estimate, and then using this pre-trained diffusion, being able to like do bias correction, give more physical realism, and doing an ensemble at a cheap cost. And so our hope is we are able to like extend this predictability range before it collapses to climatology. Probably having a few more days of lead time given will be no major breakthrough. So yeah, this is our first effort for this. I'm gonna also show a little bit of a work in progress for aerosol prediction. I think Albin has worked with the LEAP. I'm not sure if you're familiar with the NASA GIS model simulation. So this is what we have, and I don't have a lot of data particularly. So we just have 2 weeks of training data, 2 weeks of testing data for hourly resolution. So the setup is pretty simple. It's just a regression problem. So your input X are this bunch of meteorological variable with precipitation and black carbon emission over the globe. And the target is we want to predict like black carbon concentration here. And so using kind of like similar setup, what we have is that we have this prior estimate, which is a bit blurry if you zoom in. Maybe this is not a good kind of like representation of it, but it was supposed to be a little bit blurry. But the goal here is for us to be able to sample from the distribution quickly, so that we can have some moments that we can compute, such as expectation over it and some kind of like variance over it. So we are aiming to be able to emulate the probability distribution of the target given some input data. And this is just some results from the ensemble mean, given the ground truth and prediction over the grid cells of the globe of the testing data. And this is, if we scale it up to the logarithmic scale, this is still very much a work in progress, even though we are able to kind of like capture some seasonality. Actually, maybe there's not seasonality. I think this diurnal cycle, because it's just 2 weeks. But I think there are some challenges. For instance, like this is still pretty bad. I think so -1 is obviously not something you want to look here. For instance, like very high values of black carbon, the model is still struggling to predict, as well as like very small, probably it's just noisy data where you don't actually have a lot of like black carbon like emission here, still feels to capture, which might be good, might be bad. Might be good because there's no signal here anyway, it's just pure noise. But anyway, we are hoping to kind of like scale this up to like more data and see how we go from there. So yeah, that's kind of like the first part of like this operator learning for emulation and forecasting. Hopefully I'm not moving too fast. Let me be mindful of time. I'm not sure if I should take questions before I move to like the second part, or might be questions in chat.
If anyone has a quick question for Juan, otherwise I think we can ask at the end. But
yeah, okay.
I think, yeah, I think you're good. You don't have to rush.
Okay, got it. All right. So these are just some of the conclusions here, because I think a lot of the effort nowadays is to build bigger and more complex model. But I think our idea is whether we can have combine like, the benefits of both type of modeling approaches. Like reduced order model is good for interpretability and for less complexity and fast inference speed and so on and so forth. And can we combine it with a more complex model like generative AI, so we can have long range predictability, which reduced order model tends to have, doesn't blow up as much as a complex model, and it has high fidelity given by the generative AI, and we have a mix of both, like intermediate computational requirements, especially for stochastic and like highly variable stuff. So that's kind of like the main point of this Koopman operator learning. I think the second one is also pretty something that we are very excited about as well, where I mentioned earlier, one of the benefits of having this Koopman operator is the linearity that it endows the problems with. So just a kind of like give a very brief overview of causal discovery. So given some time series data, you want to discover some causal relationships. Normally it is represented by this graph. So let's say this is a simple coupled Russell oscillator. You have in a form of ODE, and then you can like transform it into a graph. It can be represented as adjacency matrix. So just like, the relationship if there's like 0, 1, 1, let's say, because there's no contribution of X to itself. So something like this. We can always convert ODE to kind of like a graph. And the goal is to be able to discover this structure given some observations, because normally we don't have these closed form solutions from observations. So this is extremely challenging. So what we have is that we are leveraging ideas from Granger causality. So the Granger causality is pretty elegant. So in a more hand-wavy way of describing it, if you have cause and effect variables, you have this like magic ball, and cause actually affects the effect variable. You'll see that the prediction of the effect is going to improve because you include the cause variable. So that's kind of like the basic idea. Whenever you include an actual cause variable, it'll always improve the prediction of the effect variable. So we are extending this to Koopman causality. So the general idea is that you have these two models at a given time t, and then you have like some latent embedding of these two models, and then you train these Koopman operators, which in our case is actually simple. It's just this factor versus a factor of times t plus 1, let's say, and then you just take the inverse of it. So it's just a linear operator of k applied to t, factor at times t, to give you a factor of times t plus 1. So just a step forward operator. And then you make a prediction of at some times tau in the future. And then there will be a forecast error, and this will be measured as the causal measure. So this is in spirit similar to Granger causality, but there's an additional step here where we do the linearization and we enforce a lot of like stuff to make sure that it follows like the Koopman theory here. So this linearization step becomes the bottleneck for causal discovery in nonlinear systems. Whereas previously in just like Granger causality, you don't have this initial step. You just like compare on the state level the error here. But those things are hard because, as you guys probably know, in nonlinear dynamics, those conclusions are always local. It can never be global. But once you have a linear systems, you can encode it in a matrix to to have it propagate into the future, and you can compute the eigenvalue, eigenfunctions, and you can compute like how fast, how slow the modes are. So these are some aside. And our contribution is showing this theorem where the causality in the Koopman space translates to causality in the data space. So I think this is one of the important theorem because like without this, it's hard to verify. It's hard to translate whether this causal measure can be used in the actual data variable space that we are interested in. So this is just a simple climate application for, let's say, toy on ENSO problem. This is one of the more popular genes ENSO model where you have sea surface temperature and sea surface height. And if we kind of like remove the nonlinear term, we linearize the whole systems. We can do linear stability analysis. So the figure here on the left is just we vary the parameter mu that we are interested in, and then the eigenvalues, and we can kind of see the regime, the stability regime, given the parameter mu. So let's say the stable bifurcation point is at 2/3, given our set of other parameters that we kind of like keep it fixed. But in other regime, let's say a little bit lower than that is a dissipative regime, and then this is a little bit more exponential, and this is it just goes haywire. It just tips the whole systems. So this is kind of like linear stability analysis, and what we want to do is whether our causal measure is able to detect this regime change, which is extremely important for tipping point detection, let's say. So this is our experimental setup. We generate the observables. So if you remember, it's the transformation from X to Y, where the systems appear linear. We can do a few things. A lot of literature use RFF, so it's prescribed. There's no learning here. We can also use autoencoder like MLP encoder and MLP decoder, and we just extract the latent space, which is our transformation. So the experimental setup, the operator K here is just a pseudo inverse. So there's no neural network learning here. And the causal measure is estimated given our kind of like sketch setup earlier. So on kind of like the top row here are the different regimes and their oscillatory behaviors. This is color coded in time. So this is the stable one, and this is the blowing up one. And our causal measure is measured against the time shift in time. And we can kind of like detect the stability of the systems given the transformations that we have using our causal measure here. So that's pretty positive. So it's able to detect kind of like stability regime in these toy problems. So this is a proof of concept. What we want to do is we want to extend this to real ENSO observations. So we are using this reanalysis product, monthly reanalysis product for over 40 years. And we also extracted like these two variables, SST and SSH, in this NINO 3.4 region. And this is the figure on the right here is just the SST anomaly that we observe from this reanalysis product against some backdrop of color-coded ENSO events, so El Nino and La Nina, which is derived from the SST anomaly index. So what we found is that we are able to kind of like detect some major events from our causal measure pretty accurately, given some ensemble of prediction here. And so this is something that is also promising. And I think this is also paving the way for early detection of tipping points, which is something that we are actively exploring as to how we can detect those. Maybe it's through gradient change of this causal measure and so on and so forth. So because our Koopman operator is dynamics, by construction, because we are trying to learn this linear operation in the dynamical space. So we can also do forecasting once we learn this K matrix, and we can like propagate the systems in time. And so these are just some proof of concepts where incorporating non-causal variable is actually making the prediction a lot worse. But if you incorporate causal variable by extension, it should improve kind of like the forecasting of the model. But we are not really exploring this yet in our paper. But in the future, we can think of probably a unified emulation that is based on like causal like principles, where maybe we retain some variables that we think is important, and hopefully that improves forecasting because we remove some spurious correlations in our forecasting problems. And also, of course, like causal discovery have to come with this full graph discovery capability, which currently is still in progress, but hopefully we are hoping to release like the package. If you guys are familiar with like PCMCI from Germany, then we are also thinking of like having similar API where people can just feed in their time series data and be able to come up with this causal graphs. So we are extending this to simple problems where we only have 3 nodes in Russell oscillator, and we are also extending it to XRO model, and we are benchmarking against some of these state-of-the-art causal discovery methods. So yes, that's kind of like what I have in terms of like operator learning and causal inference. So just a brief conclusions here. We are hoping to be able to extend this to tipping point, for instance, due to anthropogenic emission for a lot of the climate systems. So yes, that's about it. Thank you.